The broadcast is now starting. All attendees are in listen-only mode.
Hi, and thank you to all of those who are joining us this morning for this, which is the fifth in our series of webinars that are discussing limit state products, their features and their applications. For those of you who haven't been to a previous webinar, then my name is Tom Pritchard. I'm the host for today's event, and I'll be introducing this and also doing a quick roundup at the end. This webinar today is entitled Modelling Soil Reinforcement with Limit State Geo, and what it's going to do is discuss Limit State Geo's engineered element material and how it can be applied to a wide range of soil reinforcement problems, mainly today I think things such as soil nails and geotextiles. The main part of the webinar itself will run until approximately 10 AM UK time, so about 50 minutes, and will include 10 minutes at the end for questions. These can be posted via the chat functionality that's present in your webinar interface, and we'll try to answer as many questions as we can in the time available, but this isn't always possible, and yes, sorry in advance if we're unable to get to your questions. As always, I'd just like to request that anybody who has very specific questions regarding the software which might require us to take quite a long time to answer, then you're more than welcome to contact us outside the webinar via info@limitstate.com, and we'll be more than happy to answer these in detail for you. Speaker today is Dr. Colin Smith, who is the Limit State Geo Product Manager. So without further ado, I'll pass you over to him.
Okay, thank you very much, Tom, for that introduction. Good morning to those of you in the European time zone, and good afternoon or evening for those of you joining us elsewhere in the world. As Tom has mentioned, my aim today is to show you how Limit State Geo can be used to solve reinforced soil problems, and how it differs from other methods, and how to model a number of specific scenarios. So I'll be using a mix of PowerPoint slides and the software directly to illustrate the key points. And as it's a problem-specific webinar, I'm going to focus on showing how the software can be used to solve soil reinforcement problems, so therefore I might be skipping over some of the details of how to use the software, but the process should be clear. So what we're going to run through today, a little bit of background to Limit State, then we'll look at the reinforced soil modeling process in detail with a couple of examples, as I said, and wrap up with a summary of key issues at the end and some questions. So for those of you who are new to this webinar series, it's probably useful to give you some context of the software and the company Limit State. The University of Sheffield has been conducting research into limit state analysis and design and the use of optimization in civil engineering for almost 2 decades now. And Limit State was spun out from the university in 2006 with the aim of making this research available to industry. Clearly, industry users want not only powerful tools but ease of use and support, which is exactly what Limit State can provide. Limit State also has sophisticated testing systems in place. That means every time the software is run, we run almost 1,000 tests automatically to make sure it still does what it's supposed to do. The company has 2 products at present. First one is Limit State Ring, which is used for modeling masonry arches, and the second product is Limit State Geo, which is the subject of this webinar. Now, just to set the software in the context of currently available software, on the one hand, top left-hand corner of this diagram, we have software based on conventional processes or approaches such as a method of slices or specific retaining wall software, and then at the other end of the scale for more complex analysis, on the bottom right-hand corner here, you might be using finite element software where you can model any problem geometry and complex soil behavior, but typically that requires more expertise to use. And filling the gap in the middle, we like to feel is computational limit analysis. It provides an ultimate limit state analysis capability, which is a geometry flexibility of finite elements, but the ease of use and simplicity of the traditional methods. So the only parameters you really require are sort of cohesion, friction, and unit weight of soils. And if you're going to model soil reinforcement, then you need additional parameters relating to that. As I said, the software is fully flexible. You can model any geometry, so this slide just shows a range of problems that can be solved. And we're going to be focusing primarily on the reinforced soil problem, an example of which is given in the middle here. So just a little bit of background to reinforced soils, just to put the context of how this is modeled in the software. Soil reinforcement can be considered to work by adding tensile strength to the soil. As we know, soil is fairly poor in tension, or equivalently, it's a way of transmitting tensile stresses from one part of the soil body to another. And we can incorporate reinforcement as one or two-dimensional items. So in terms of one-dimensional reinforcement, I'm talking about things like soil nails, whereas two-dimensional reinforcement, we're talking about sheets, which could be geogrids or geotextiles. And a whole range of applications, just put three examples up here, soil nailed slope, a reinforced soil wall, and a reinforced embankment. And we'll look at two of these examples later on in a bit more detail. So how are these types of problems analyzed by sort of traditional classic approaches? Well, we can use a number of methods, such as the method of slices for slope stability analysis. And we can try and apply that method to a reinforced slope. So we will assume a particular slip surface shape, split that up into slices, and if we have a reinforced slope, then for failure to occur, we're either going to have to pull the reinforcement out of the stationary soil behind the sliding surface, or that will stay still and the sliding mass will have to pull out of the reinforcement on the other side of the slip surface. If you know what the shear resistance around the reinforcement is, then you should be able to calculate what the pull-out force is at failure, and then this force in the lower diagram can be applied to the slip circle analysis, and that will give an enhanced stability to that particular sliding wedge of soil. An alternative method that's commonly used, one or two wedge analysis, where you're looking at a reinforced soil mass and consider a sliding wedge of soil. And again, if that sliding wedge or that interface crosses the reinforcement, then in order for that wedge to slide, it's going to have to pull that reinforcement out. And again, you can calculate that resistance and apply that to the sliding wedge, and again, that enhances the stability. So the key thing for us is, how is that restraining force calculated? So the kind of basic level for undrained soils, if we have an element of reinforcement that's being pulled out through the soil, then we might assume that the resistance, shear resistance on the interface, is equal to alpha Cu, where alpha is an adhesion factor, and that will reduce, make an allowance for the fact that the sliding of the reinforcement on the soil is not going to give you the same shear resistance as sliding the soil on itself. So for a 2D reinforcement, sheet type reinforcement of length L, then the pull-out force is going to be 2 alpha CUL per unit width. And the number 2 comes in because we've got shear top and bottom of the reinforcement surface. For one-dimensional reinforcement, say a cylinder, we take the circumference of the cylinder and again multiply that by alpha CUL to get the pull-out force. So in both cases, if we were to write that in a very general form, we can say the pull-out force is equal to some constant Tc multiplied by the length of the reinforcement, and Tc depends on the geometry and interface characteristics. For drained cases, it's pretty similar, except we've got frictional interface, so instead of alpha Cu on the as the shear force mobilized on the interface, we've got alpha multiplied by the normal effective stress multiplied by tan of the angle of friction. And again, for two-dimensional reinforcement, we just multiply that up by the area, and for cylindrical reinforcement, we would multiply again by the circumference and the length. Now, it's a little trickier for drained analysis because estimating the normal stress is a little more complicated. Quite often it's just assumed that that normal stress is equal to the acting vertical stress, which may be calculated from simple statics, unit weight of the soil minus the pore pressure multiplied by the depth, And for a one-dimensional cylindrical reinforcement, this estimation may become more complicated because the stresses are acting all the way around the cylinder, so they're not just the vertical stresses, you've got horizontal stresses and so on. But again, there are various ways of trying to estimate what that would be, and that just becomes a modification factor on the vertical stress. So the upshot is that in many conventional analyses, the pull-out force is simply some constant, which we call TQ here, multiplied by the vertical stress multiplied by length. And this is essentially, these types of equations are essentially what we're using in limit state geo to calculate the reinforcement interaction. So we'll look at that in a little bit more detail. Before we do that, it's probably worth recapping how limit state geo works. So if you haven't seen the explanation before, this will clarify how the limit state geo software actually solves collapse problems. If you've attended any of the previous webinars, then this will be familiar to you. So the software uses a relatively new numerical technique called discontinuity layout optimization, which can be used to provide rigorous upper bound plasticity solutions. It's a direct way of analyzing the collapse state and came out of a 5-year research program carried out at the University of Sheffield, and the key publication which outlined the method was given in the Proceedings of the Royal Society in 2007, and there have been a number of other publications since then looking at further developments of the method. In essence, it's quite simple to explain. What we do is, if we start with a problem which is a bearing capacity of a rectangular block of soil, so we have a load on the surface and a block of soil here. Instead of using elements as in the finite element method, we populate the problem domain with nodes. So here we've got 12 nodes. And then we connect every node to every other node with a potential slip line. And using optimization techniques, rigorous optimization techniques, we can then feed that into a linear optimizer and get that to pick out from that set of potential slip lines, which if there are 12 nodes, will be 12 multiplied by 11, 132 possible slip lines. Out of that set, we can use optimization to pick the critical few slip lines that form the critical collapse mechanism. And so the more nodes you have, the better or more accurate your collapse mechanism. So often you might be solving with 1,000 nodes, which gives you 1,000,000 possible slip lines, and out of that set of 1,000,000 possible slip lines, the optimizer will pick out the critical subset that gives you the collapse mechanism. So it turns out that that can be reduced to a linear optimization problem, which is easy to solve using modern linear optimization software. And once the problem is solved and those critical slip lines are identified, the software is then able to put the lines together to form sliding blocks and wedges, which it can then animate to help interpretation. So here we have a reinforced earth wall. Various sliding blocks moving in this animation to help illustrate what the critical collapse mechanism is. We'll look at this in a bit more detail in a moment. But the key point is to bear in mind is that increasing the number of nodes in the problem allows more potential slip lines, and there's a more precise mechanism to be identified. So just picking up more detail about how this would work with soil reinforcement. If we're going to model reinforcement in the software, and this reinforcement in this diagram is represented by these green lines, then what we see in this collapse mechanism is that we have not just one sliding wedge, but we have several sliding wedges, and we've got different relative movement between the soil and reinforcement in different places. It's not as clear-cut as in conventional analysis, where we have perhaps one length of reinforcement which is pulling out and the other length of reinforcement which is staying embedded in a sliding mass. We could have relative movement right across the board. So we have to be able to model that. In this particular case, we've got this more complicated behavior near the top of the mechanism. We have straightforward pull-out at the top here on the right, and at the base here we've actually got the reinforcement pulling out of a wall element. But we need to be able to capture all of this in a very general way. So what the software does is it doesn't try and separate out lengths of reinforcement which are pulling out, lengths which are staying embedded in soil and are stationary. It just simply says what is the relative movement of the soil with the reinforcement at any local point. So here we've got an example of a wedge of soil sliding down past a piece of reinforcement. There could be many of these sliding in different ways relative to that reinforcement. If we know the relative movement, we can calculate the limiting shear force applied to that reinforcement element over its that short length, and carry that calculation through to a force taken by the reinforcement. And that would be calculated using this equation, the second equation there, which is essentially using these parameters TC and TQ that I referred to earlier on. And that allows us to produce a very general implementation of soil reinforcement interaction. So how do we, how does that work? Well, it's probably useful just to look at some simple element tests to illustrate these principles in a bit more detail. So what I'm going to do here is escape from that software, and we're just going to run an example, run the software now, which is this one. So this is the Limit State Geo software. So if you've not seen that before, if this is new to you, I'll just give you a brief overview. So the problem itself is clearly illustrated in the middle of the diagram. Anything we click on, its properties appear on the right in this property editor. And if it has geometrical properties, its geometrical properties appear below here in the geometry editor. And we have a number of menu items and buttons which can control the software in various ways. And we also have this item here, Materials Explorer, which allows us to use a whole range of different materials, and we can create new materials if we wish. We can also create water pressure regimes, which we're not going to look at today. There isn't time. We're going to focus on the reinforcement. So what we have modeled here is two reinforcing elements. Oops, if I click on that one there and this one here, embedded in blocks of soil here and here, and actually embedded in a rigid material here and here. And this is a very simple pull-out test. Effectively, this material here and here is, you could imagine, is solid concrete or very rigid, and the reinforcement here is just embedded in that and is stuck to that. We're applying a force here to pull it out, and so what we're interested in really is how this piece of reinforcement interacts with the surrounding soil. And in the software, the reinforcement elements are modeled on boundaries, so these are boundaries in the problem, but wherever you draw a boundary between two blocks of soil or whatever, you can place a soil reinforced element. These are called engineered elements in the software, and we've got two of them modeled. We can access them in two different ways. If I click on this one here, its properties appear on the right, and in this materials part of the table, we see we have what is called top and bottom materials. These are interface materials which we're not going to use at the moment, so we'll ignore those. Those should be left empty for this particular case. We're going to look at the engineered element itself. And in this particular example, we're looking at how we'd use an engineered element to model, for example, a one-dimensional reinforcement such as a soil nail. So this is called reinforcement element 2, and if we look at that, we have a pull-out factor of 10. This is the value for TC, so that means that the overall pull-out of that reinforcement is 10 kilonewtons per meter length. We've set other parameters to 0. We'll look at those later on, but TQ is set to 0. That's a frictional component. These components we'll look at later, and as we'll look at these ones later too. So basically, it's got a pull-out factor of 10 units per meter length. This piece of reinforcement here, again, I can click on its properties here, has been given a pull-out factor of 1 times 10 to the 30, effectively infinity, and that basically means that it will not pull out of the material that's adjacent to it, so it's effectively firmly bonded into this material. We've set up a load on the left here. This is effectively a unit load, so what we're going to ask the software to do is tell us what we have to multiply this unit load by to get collapse of the system. And if I click solve here, we get a diagnostics message which gives us a little bit of information. We'll ignore that just for the moment, and the software will actually solve the problem, and it's a very simple problem, so very quickly it shows that it says we need to apply a load of 20. That's the result given down here, or also here, to this block in order to pull that reinforcement out. And the 20 would seem to be the right answer, because this block, which I've just clicked on, its geometry showing runs from x coordinate 2 to 4, so it's 2 meters long, and as we showed before, there's a pull-out factor of 10, so we'd expect it to pull out with a load of 2 multiplied by 10, which is 20, which is exactly what we've got. And the software also can be set up to plot axial force, shear force, or moment in any engineered element. So for soil reinforcement, we're generally interested in the axial force. And so it's showing, as we'd expect, that the axial force is going to be 0 at this end, and slowly it's going to build up all the way to 20 at this end as the shear force from the soil is applied to the reinforcement along its length. Now, just to be clear, run through a few more examples. So I'll change the property of that reinforced element. As I said, I can access it by clicking on it directly, but it's also defined by this material R2 here, so I can click on that material directly and see its property there, which is 10. So if I increase its pull-out factor to 20, then of course we would expect the pull-out force to go up to 40. That's 2 meter long as before, so it's 2 times 20. And as we expect, we get 40. I'll increase its pull-out force to 100 now. Oops, 100. So we'd expect to get an answer of 200. We in fact get an answer of 120. And the reason for that is, of course, that the engineered element cannot pull out with a greater force than can be sustained in shear by the surrounding soil. If I click on this block of soil, or this block, the properties appear here, and we have a material there which is called soft clay, and that clay has an interface, or has a shear strength of 30. So it's not possible for that reinforcement to pull out with a force greater than the resistance that clay could provide if that reinforcement was a sheet. So it's limited by that value of 30 multiplied by the length 2 and multiplied by 2 because we could have shear top and bottom. So there is a limit there, but generally you will of course be setting this value lower than for one-dimensional reinforcement, lower than an equivalent sheet would be. So I'll change that back to 10 and we'll run that. So we get back to 20. So the other thing to say is, of course, that if the reinforcement has a strength lower than 20, then it will actually rupture. At the moment, we've set the rupture strength of this reinforcement, I've clicked here, to 1 times 10 to the 30, which is effectively infinity. If I set that to 10, we should find that the reinforcement will fail in rupture before it can mobilize the full shear resistance. And so here you can see that we've got a result of 10 now, and that this shear force is building up to a maximum of 10 at this point. And the way that's represented in the animation is basically the reinforcement just stretches. Whereas previously, if we looked at the animation, if I change this strength back to something very large, you can see that the reinforcement pulls out of the soil at this end. So in the animation, it will indicate whether you're getting pull out, so you can see a gap forming at this end, or whether we're getting rupture, which is effectively represented by the reinforcement stretching in the animation. So that's a representation of the pull-out force. I'll just touch on one other property of these engineered elements, which are not typically used in classic analysis, but if you have a one-dimensional element such as a soil nail, if the soil is moving past the nail laterally, then there might be a lateral resistance in the same way that you get a lateral resistance of a pile. So you can specify that in this particular problem. If I click on this item here, we have what's called a lateral factor here, which effectively works the same way as the pull-out factors, except it responds to lateral force. So this is basically saying that for soil to move past this reinforcement laterally requires a force of 25 kilonewtons per meter length of the reinforcement. So this element test here is simply set up a little jig really with some rigid elements to apply the forces, and we're asking the software what do we have to multiply these unit forces by to cause collapse. So we run that problem and we get an answer of 75 in this particular case. This element is now moving sideways through the soil. We're actually plotting shear force in the element here, which is running from 37.5, minus 37.5 to 37.5 at the other side, which is basically equivalent to that overall force of 75. And why is it 75? Well, if we look at the reinforcement, we see that it's modeled from a coordinate x 4 to 1, so that's 3 meters long, and we had specified it as a lateral resistance of 25. So it is possible to model lateral resistance. It's not necessarily typically used in conventional analysis, so you can simply set those values to 0 to eliminate that process. We actually recommend that you set that to a very small number like 0.1, something like that, simply to stop occasionally you get anomalous results where if the reinforcement isn't asked to do anything and it has no lateral resistance, then it could simply float out of the soil. But a very small number there will just prevent that happening. So that's the element test. So how do we actually apply that to an actual problem? So I'm going to jump back to our PowerPoint presentation. just give a quick summary of what we've covered there. We can model frictional and cohesive pull-out resistances per unit length. We look primarily at the cohesive ones there, but the frictional properties can be put in and work in conjunction with the nominal vertical stress. We're following pretty much the same mechanics as you find in many conventional analyses techniques. We can model lateral resistances, but you may wish to set those to 0, or to a very small value just to prevent floating the reinforcement, and we can specify tensile rupture strengths for reinforcement. Okay, so we'll look at an example of modeling a soil-nailed reinforced slope. So this is from a study published by Clark et al. In 2013. And here we're modeling a slope frictional material with a small cohesion of 2.5 kPa, angle of friction 26 degrees, with some soil nails of diameter 0.25 meters, taken for simplicity an interaction coefficient of 1, and a horizontal spacing of 1 meter. So every nail, every spaced every 1 meter horizontally. We can calculate these coefficients TC and TQ by these equations. So the circumference of the nail multiplied by the interaction coefficient multiplied by the cohesion intercept divided by the spacing, and that gives us a TC value of 1.96, and TQ is the frictional property, and that comes out as 0.383. And here we're just, for simplicity, assuming that the normal stress on the nail is equal to the nominal vertical stress at the level of the nail. So in this particular model, at any point on the nail, the software works out the height, the depth to that point, and multiplies by the unit weight of the soil, which is the same process that is carried out in most conventional analysis. Oops. So that's what we're going to model this problem. So we'll jump back to the software and that model. So here we've got the limit state model of that diagram I just shown you. If we click anywhere on here, then we get the soil. So you can see it's got a C dashed of 2.5 and a phi dashed of 26 degrees. And the reinforcement nail, if I click on that, you can see that it's got pull-out factor of 1.96 for the TC value, and TQ is 0.383. So if I run that analysis, I get a particular collapse mode, and you can see there's a lot of sliding wedges in between the reinforcement, but the overall shape is pretty much like a two-wedge analysis, but the software is finding the critical collapse mode in that case. And we can do things like changing the length of the nails, so I can shorten these down, perhaps see what effect that has. And if I solve that, we'll get a somewhat different collapse mode. And what I'm doing is I'm asking the software for any ultimate limit state analysis process, and we've gone into this in more detail in previous webinars, but essentially we're asking the software, what do I have to do to this system to cause collapse? And we can ask that question in two ways. We can say, how much do I have to increase an existing load in the system to cause collapse? Or alternatively, how much do I have to reduce the strength of the soil by to cause collapse. In this case, we're asking the question, how much do I have to increase the unit weight of the soil by to cause collapse? And what the software is saying is you have to multiply the unit weight of the soil by 0.98 in this case to get a collapse mode, which means that this system is pretty much on the point of collapse. Before I shortened those soil nails, we had a factor of 1.2, which meant that basically we had to multiply the unit weight of the soil by 1.2 to cause collapse. And further details is in the manual of how you set these various, how you define what you want to the software to scale to cause collapse, but you can choose any load or any combination of loads, or specify that you want strength factoring. So that's a kind of brief look at modeling the soil nails and how they interact and how that interaction changes, but certainly that increases the stability of the system. And if we just jump back to the presentation, in that paper by Clark et al., first of all, we looked at modeling comparing the DLO analysis, or limit state geoanalysis, with a two-wedge analysis. And first of all, just to check that it did work validly, the DLO analysis was set up so it was forced only to model two wedges. Normally, as you've just seen, it will model hundreds of wedges, but you can set it up and force it only to model two wedges. And that was compared with a sort of classic hand calculation using two-wedge analysis. And this graph shows a comparison. The curves are from the traditional analysis, two-wedge analysis, hand calculation. The individual data points are from the DLO analysis, and you can see that they exactly match up. So that indicates that the reinforcement modeling is doing exactly what it should do. If you then actually allow the software to pick whatever collapse mechanism it wants, then what you find is, if you're trying to compare this first graph, which is basically showing the required friction angle for a given length of reinforcement here, just to avoid collapse, this is what a two-wedge analysis would give you. And the software is finding more critical mechanisms, so it's actually saying this is a bit over-optimistic, and really you need to be looking at a slightly stronger soil to prevent a more refined collapse mechanism and a more critical mechanism than the simple two-wedge approach. So what the software can do is essentially seek out and find the most critical collapse mechanism. And it's not restricted to two-wedge or one-wedge or whatever. It will find whatever mechanism it can that it can construct out of slip lines joining the nodes that you've specified. So you can see in this diagram here there are a very large number of nodes, and so the software is able to pick out some very fine mechanisms there. And it will find, if internal failure is critical, it will find that. If external failure is critical, it will find that, and so on, or any combination. So in summary, if we're modeling one-dimensional reinforcement like soil nails, the implementation that we have in the software allows soil to flow past the reinforcement. It doesn't behave like just putting a sheet in the soil. Soil can flow past the reinforcement, but the reinforcement can still take some of the tensile forces through the soil. It's been calibrated against two-wedge analysis, and the recommended approach to modeling 1D reinforcement is to use engineer elements, calculating TC and Q pull-out values and entering those. You may specify lateral coefficients if you wish, but they may be set close to 0, and you would specify a tensile rupture strength as appropriate. And generally, as we showed a little earlier, you can set boundary materials above and below the element, but they were not set in this particular case. So normally we just leave those as empty, essentially. So that's using modeling 1D reinforcement, and the way the formulation works, as I've said earlier, is that it allows the soil to flow past the reinforcement. If we're going to model two-dimensional planar reinforcement, like sheets of geotextiles or geogrids, then generally the soil is not going to flow through the reinforcement, and we are perhaps more concerned that we might have sliding above the reinforcement or below, and that may be the same amount of sliding above and below, or it may be different. So we take a slightly different strategy in this case. And again, I'll just jump back to the software to look at how we deal with that particular case. So here we have an example very similar to the previous one that I looked at. We've got the same block mechanism on the left to allow us to pull out this length of reinforcement. This time this reinforcement has a length of 1.5 meters. And we have this engineered element, which this time I'm setting the pull-out factor for TC to be a very high number, effectively infinity. I can set both TC and TQ to infinity, or just TC, it doesn't matter, they will override effectively their infinity. I'm setting the lateral factor to infinity, and in this case normally we would set the moment of resistance of the material to 0, and that effectively means that we're modeling it as a very flexible material. It has no bending moments, it's free to bend in any way that it likes. The rupture strength here we're setting as infinity for the moment, and what we want to do for this engineered element is, if we're going to model it as a sheet, the fact that we've set the lateral factor to infinity prevents soil flowing through it. The fact that we set the pull-out factor essentially locks it to its top and bottom interface materials, and so we allow all the interface action to occur through those. So at the moment we don't have any material assigned, and what I'm going to do is assign a material that relates to the surrounding soil. So this surrounding soil is a clay soil, and it has an undrained shear strength of 50. So I've created what I've called interface above material, and we can set materials in the software as what we call a derived material, which is a material derived from another one but with its properties scaled. So it has a parent material here, which is the clay that we've just mentioned. It's in the soil surrounding the reinforcing element. And what we're saying is actually the strength of this derived material is 0.9 multiplied by the strength of the parent material. So effectively we're saying the alpha factor, interface factor here, is 0.9. So I'm going to put that interface above material on top of this engineered element. So if I click on this box here, I get a button that says change, and that allows me to assign material. So I'm going to put interface above on that. I also have an interface below material, and in this case I've said this is an unusual reinforcement element. It's actually rougher on the top and a bit smoother below. It's got an interface factor of 0.6 relating to its parent material, which is still this clay of strength 50. So you've got the flexibility to do that, and of course if you've got a different soil above and below the reinforcement, then you can choose those properties as required. So I'm going to click on this bottom element and assign the interface below material. So if I zoom in on the element, you can hopefully see that it's got this 3 colors on it. The interface above material, the element itself, and the interface below. And what we've done by setting the pull-out resistance of the element to infinity is we've locked it to those interfaces effectively. So when I run that problem, what's going to happen is the reinforcement is going to slide on those interfaces and be pulled out as before. This time I'm getting an axial force of 112.5. Now the clay, original clay, had a strength of 50, and I've applied factors of 0.9 above and 0.6 below. So on average that's 0.75. So effectively per unit length I've got 37.5 applied to that. And the length of the reinforcement is 1.5. So if we factor all those numbers in together, then we end up with this load capacity of 112.5. It's perhaps easier if I were to set these values to say 0.5 and 0.5 there and below to a half. So effectively we've got half the interface friction above and below, and we run that problem. So if I have half the interface friction above and below, I've got 25 above, 25 below, and a length of 1.5. So all multiplied up comes up to 75 for my pull-out load. So we can set the planar reinforcement interaction in a different way. This way, the rupture strength still behaves as normal. If I set the rupture strength to say 24 for this material, then of course it will rupture at a strength of 24 rather than 75 in this particular case. So I get a result of 24. So the software will allow that rupture to occur. So that's a brief overview of modeling planar reinforcement, and if we jump back to the PowerPoint. In summary, we can model it as a flexible engineered element with infinite lateral resistance and zero bending strength, and we just specify the interface properties directly. And that allows differential shearing above and below the reinforcement. And again, we can specify tensile rupture strengths. So we'll finish off this webinar by looking at a reinforced embankment. So often if you're going to build an embankment over soft soil, you'd use reinforcement between the embankment and the soft soil. And there might be a whole range of questions. What slope angle can you have on the embankment? How strong should the embankment soil be? How high can you build the embankment? What's the required rupture strength for the reinforcement? Now, you can analyze this using method of slices or a slip circle method, but that will only capture one type of failure mode, and that may not be the critical failure mode. So this diagram here is trying to show a slip circle method, a rigorous sort of upper bound where you have a log spiral in the granular embankment and a circular arc in the underlying clay. So we'll just jump to the software again and look at an embankment model. So here we're modeling half an embankment. We've got a symmetry line down the middle. We're modeling the embankment material as a granular frictional material, friction angle 32, C-1/2, and we're modeling the base soil here as soft soil. It's got an undrained shear strength of 16. The geotextile itself, we're modeling all those coefficients, lateral and pull-out forces, as infinite effectively, so they're locking themselves to those interface properties, zero moment of resistance and a rupture strength of 25 to begin with. And this element itself has top and bottom materials. The top boundary is defined as having an alpha factor of 0.8, so that's 0.8 of the strength of its parent material, which is the overlying sand. And the bottom boundary, again, we've got 0.8 of its parent material, which is the underlying soft soil. So if we solve that, we're going to solve this in what's called factor strength mode. So we're asking the software, what do we have to factor the strength of the soil by to cause collapse? And what we get is a mechanism that looks reasonably similar to a sort of slip circle type mechanism that we would get. And we can also see the software can plot the axial force. So we're actually seeing that we're getting rupture in this reinforcement in this particular case. And we've compared this with sort of slip circle method of slices approaches, and we get very similar answers in this case. But what the software is able to do is obviously pick up different types of failure modes. So if, for example, we made the rupture strength of the reinforcement much higher, put that to 250, really effectively way beyond its failure, then we can get different failure modes. So by making that much stronger, what we find is that once the software has found the critical failure mode for factoring strength, we just get a simple slope failure in the embankment. So the software can identify those failure modes. But additionally, supposing the soft soil was even softer, just for the purpose of illustration, I'll half that strength. The software again can find different failure modes. So in this case, it's finding a collapse mode, which is effectively squeezing the underlying clay, and the embankment is in effect snapping itself down its middle and rotating into that clay, as we'll hopefully see in the animation. So again, hopefully this shows the power of the software to find the critical collapse mechanism. It's not restricted to predefined modes. And generally it's finding more critical mechanisms that a slip circle method would find. So to wrap up then, in terms of planar reinforcement, we've got a generic implementation which is available in the software. We've compared it against method of slices and slip circle analysis, and the recommended approach is to set the pull-out and lateral coefficients to infinity, specify tensile rupture strength, and define the use of boundary materials above and below to effectively implement the alpha interface factors. So that pretty much wraps up this webinar. So to summarize, hopefully you can see that we've used reinforcement modeling in limit state geo using the same mechanics as conventional methods, such as a two-wedge method, but effectively we can model thousands of wedges. There's no need to separately consider internal-external failure, pull-out lengths, or reinforcement rupture. Those are all captured in the one analysis, and the method automatically searches all possible failure modes every time you solve. And we have a flexible geometry and load definition. We can model 1 or 2D deformation, and with a 1D representation, soil can flow past reinforcement, which means that things like soil nails are not being modeled as sheets in the model, whereas in 2D we can model them as sheets, but we can allow differential movement of soil above and below if required. So that wraps it all up. I'll just put the sort of normal slide I put up at the end of the webinar as a general point about the software. Hopefully you've seen, as I've used it, that it's an interactive piece of software, solves quickly, allows you to answer what-if questions, give you a better feel for a problem, and we can deal with pretty much any ultimate limit state problem type without having to impose idealizations. So, I think we will move on to questions at this stage. And if you just bear with me. Okay, just bringing up the questions. So I have a question on the reinforcement. Can an engineered element be fixed to the outside boundary for an embankment where we're modeling symmetry and pull-out is not a realistic situation apart from limiting tensile strength? Okay, if I've read that question right, I can illustrate that actually using this model here. Generally if reinforcement is meeting an external boundary, there is no fixity there. You have to put that in specially. So what I've done here, it's actually hidden away, but if I zoom in, I've actually attached this reinforcement here to another length of reinforcement here. Wherever reinforcement joins, they are locked together, and this bit of reinforcement is essentially attached to this rigid block of material. So that is effectively giving me fixity of this reinforcement, this length of reinforcement at this point, because it's joined to this, which is rigidly fixed to this block. And this block itself is actually, you can't see it, but there's a fixed boundary here. So this is rigidly fixed. And what I've done is I put a frictionless interface here in place, so that effectively emulates a symmetry boundary condition, which is what is presented above and below there. So I hope I've answered that question as it was asked. Yeah, second question. So for a geotextile, should a higher lateral factor be applied to prevent soil passing the continuous reinforcement? Yes, that should. Essentially, we would recommend you apply a infinite lateral resistance and set the bending moment of the engineered element to 0 to allow it to effectively flex and move with the soil, but for the soil not to move through it itself. Okay, just looking to see if we have any further questions. Sorry, just bear with me. I'm trying to... Okay. I think that's wraps up the questions for the moment. So what I'm going to do is pass back to Tom just to wrap up the webinar. And if you do have any further questions, then please feel free to email those through, and we can answer those. So I'll pass over to Tom now just to wrap up.
Yeah, thanks, Colin, and thanks everybody for listening. Now, near to the end of the webinar, we hope you found it useful and informative. For people who aren't actually current users of the software, then obviously we hope you found something new about it. And if the webinar's prompted any questions from anybody at all, please do just get in touch with us via telephone, or you can email us on support@limitstate.com, and we'll be more than happy to answer any questions for you about that. If you would like to watch the
Unmuted.
webinar again, then